Chapter 6, Sections 1 and 2, Graphs of Relations and Linear Relations. This video we're actually going to focus on linear relations, what they are and how to identify them. So we have three graphs, and it asks us to plot each of these three relations, and then we're going to describe them below as linear, nonlinear, or continuous, discrete. I'll explain what they mean in just a minute. Right. Well, let's just plot this one. Here we have 4 points given. These are the only 4 points given. So let's plot them. This represents the x-coordinate, and this represents the y-coordinate. So this is called an ordered pair. So -5 means we go left 5, and -4 means we go down 4. So we put a dot right there. And you should be familiar with how to plot these. Next, -1, -2. That's left 1, down 2. Okay. 3, 0. It's right there. So we go right 3, and y is 0, so we don't move up or down at all. And the next one is 7, 2. So it's right 7, up 2. Now some of you might want to jump the gun and just say, oh, well, here's a bunch of dots. Let's connect them. Okay. Do not connect these dots. Okay. It only asked to plot these 4 points, and only these 4 points. Okay. So you should not assume that you can connect them. All right. So first off, is this linear or nonlinear? Well, what does it mean to be linear? In a nutshell, is it a straight line, or would the points fall on a straight line? Okay. Now you don't want to actually draw the straight line, but if you were to imagine it being there, these dots would fit perfectly on this straight line. So therefore this is linear. So if it's straight, it's linear. If it's curved or it's not straight in any way, shape, or form, it is nonlinear. All right. Which is it? Is it continuous or discrete? Well, discrete means you're only plotting specific points. In other words, you're not connecting them. You're not filling in the gaps. Well, we're not meant to connect these. Okay, it doesn't say to do that. So this is a discrete relation, only specific points. All right, let's do the next one. Again, we have 4 points that we want to plot. X is -6, y is 4. So that is left 6 and up 4. So you should put a dot right there. -2, 1, left 2, up 1. And here we go right 2 and down 2. And then we go right 6 and down 5. That's right there. Okay, so these are the only 4 points that we're asked to plot. Is it linear or nonlinear? Okay, well, imagine a straight line passing through. Okay, that would clearly, these dots would all lie on that straight line, so this is linear. And of course it's discrete, because we're only plotting specific values. All right, so for the third relation, we have an equation this time. So specific points are not given, so we have to choose a few. And in this case, when we're done, we can connect them. All right, so later on in the course, you'll actually be able to look at an equation like this and immediately graph the relation without doing any number crunching, any work whatsoever. You can just plot it just by recognizing it. But we're not quite there yet. But you should be familiar with the concept of a table of values. Okay, so you choose different values of x, and you work out what y has to be, and then you plot them. Okay, so we're free to choose whatever x values we want. Let's pick numbers that are easy. Let's choose 0. Why not? So imagine x is now 0. So 1/2 times 0, that's just 0. Plus 2 is 2. Okay, so there is a point that satisfies this equation. So let's plot it right here. That's all we're doing. We're just picking points that satisfy this equation. Let's pick another one. Again, you're free to choose any x value you want, but look at what's going on here. You'd have to multiply that x value by 1/2. Well, you should know that multiplying by 1/2 is exactly the same as dividing by 2. Well, if you choose an odd number for x and you divide it by 2, well, that's not even, so you'll get a decimal. That's not wrong, but then you're going to have to kind of guess halfway between these crosshairs where the point would go. So why don't we pick numbers that are even? That way you don't have to work with decimals. So I'm going to choose x is equal to 2. Now this time I'll actually show the evaluation process. So y equals 1/2 times x, which I'm now replacing in brackets with 2, plus 2. Okay, so it's the right-hand side that I'm just trying to simplify. So as I work this out, I'm going to work down. I'm going to line up the equal sign. So 1/2 times 2, that's just 1. And then we're still adding that plus 2. And we can work that out easily. Okay, see how I'm lining up everything? And 1 plus 2 is 3. Okay, so that's our final y value. So I put that there. And that is an ordered pair, so let's plot right there. Right 2, up 3. Okay, well, we actually have enough at this stage for a straight line, but I'm going to plot one more because we need to verify that it's straight, right? More or less. So I can pick any number I want. You can choose 4. You can choose any number you want. But I'm just going to pick, I don't know, 6. Okay, it's even, so I know I'm not going to have to work with any decimals. Okay, so I evaluate it the same way, just change that 2 to a 6. So 1/2 times 6. Well, what's 6 divided by 2? That's just 3. And of course we're adding 2 all the time. So 3 plus 2 is 5. Okay, so that's the type of mental math that at this stage you are expected to be able to do quite easily. So this is right 6 and up 5. So that dot would go there. Okay, now we could keep going on and on and on plotting as many dots as we want. And then eventually they would start to blur together and you would see a line. So that's why we're able to plot a line through these points. So let's get the line option here. And that goes as best I can. Right there. Good enough. And put some arrows there. Okay. So that is our relation. Clearly it is linear. Okay. But these points are connected. So a line is actually a collection of infinitely many dots, just like these. Okay, but they're all so close together that they just blur and form a nice straight line. So this is continuous. Okay, because there's no value, okay, within this line that I've drawn that we couldn't use. All right, so without graphing, determine whether the relation is linear or nonlinear. Okay, if we were to graph it, it would be easy. Okay, if it's linear, it means these dots would lie on an imaginary straight line. All right, but without graphing, how can we tell? Well, there are different techniques, and I'll show you one of them. Let's first look at how the x values are changing. So from this x value to the next one, 1 to 2, that is a change of +1. Okay. Okay, from 2 to 3, well, that's also a change of +1. And 3 to 4, well, that's a change of +1. Okay, so x increases by 1 each time. Okay, well, that looks good, but that's not enough to verify that it is linear yet. We have to look at the y values. So we have -5 to 5. That is a change of +10. Okay, so in order for this to be linear, every time x increases by 1, y has to increase by 10. Okay, that's the rule. Okay, if it breaks that rule at any point, then it's not linear. Okay, so if we hope it's linear, this has to be a change of 10. Is it 5 to 12? Uh-oh, it's not. Okay, 5 plus 10 is 15. That doesn't work. Okay, that is a change of +7. So I don't even need to look at this one. I don't care. It's broken its rule. So this, I already know, is nonlinear. If you were to graph these 4 dots, they would not sit on a straight line. Okay, the next one, do the same thing. So the change of x, so from -3 to -1, that's an increase of 2, so I'll put +2. from -1 to 1, well, that's also an increase of 2. Okay, and we have 1 to 5. Well, wait a minute, that's an increase of 4. Okay, well, you might think, oh, the rule is broken. Well, not necessarily. Okay, because when you have dots that lie on a straight line, the dots don't have to be evenly spaced. Okay, so there's actually nothing stopping us from, pretending that there's a point in between here. You can do that if you want. In fact, why don't I squeeze that in? So what would that be? I'll put that in black. So we want to increase x by 2, so that would have to be 3. Okay, so that rule still follows. Okay, and 3 to 5, that's an increase of 2. Okay, now you don't have to do that. If you didn't put in this point, you just have a jump of 4. Okay, so let's determine if it's linear though. So if it's linear, every time x increases by 2, y has to increase by the exact same amount every time. Not necessarily by 2, but just by the same amount consistently. So from 4 to 6, that is an increase of +2. Now these don't have to be the same, but just in this case they are. So for this to be linear, this pattern must continue. So this must also be the same as that. And it is. Okay, 6 to 8, that's definitely an increase of 2. Okay, so if this were to be linear, what would this imaginary coordinate have to be? Well, if we're increasing 8 by 2, that would have to be a 10. Okay, now I'm getting kind of messy here. Again, you don't even have to put this point in here if you don't want to. All right. So, moment of truth. Okay. Last from 10 to 12. Aha. That is also an increase of 2. So we have verified this is linear. Okay. You don't have to do this, but I'll just show you what would have happened had I not put that point in. This would have been an increase of 4, and this would have been an increase of 4. Okay? But it would still be linear, because this would be an increase of 2 twice. So I'd have to have this same increase of 2, but twice as well. Okay? So either way, this one's linear, nonlinear. All right, determine which relations are linear. It says, note, if the sum of all exponents in any single term does not equal 1, for variables only, then the relation is nonlinear. Don't worry, I'll go over that. So what we're trying to do here is we're trying to figure out which of these 6 relations is linear, or are linear, which are nonlinear. Now one way, of course, is just to try and graph it and see if it's a straight line. But particularly for a nasty equation like this one, okay, that could be quite painful to graph by hand. So there's actually a very simple way to determine whether whether the graphs of these things are straight or not, just by staring at them. And I'll show you how to do that. So let's look at the first equation. I have x and 10. So we have a term here, which is x, and we have a term here. We're only going to focus on terms that contain variables, so letters. So this number 10 here, we're not even going to look at that. There's no variables attached. So we're only going to look at that one. So how many exponents do we see in total? Well, actually, I don't see any, but there's always an invisible 1 here if an exponent is not explicitly given. Okay. Well, the grand total of everything we see, exponent-wise, is just 1. Well, if it does not equal 1, it's nonlinear. Well, it equals 1, so therefore it's linear. Okay. Next one. We have, well, it's a bit uglier, but we have 2 terms that contain variables. So we're only going to look at those. In this term, the exponent, the p is 2, and the q, well, that's an invisible 1. So the grand total of exponents in this term alone is actually 3. Well, already I don't even need to look at the other ones, because I know it's not equal to 1. So therefore, this relation is non-linear. Okay, but you could look at this one. Okay, this one would break it as well. Q to the 4. Hey, that's not equal to 1. Okay, so this is definitely non-linear. All right, next, y equals 2/3 times x minus 2. So we have a term there, the variable, and this term. Okay, so the exponents off that variable, that's invisible 1, and the exponent here is invisible 1. Okay, so the total exponent value is 1. This one is also 1. Therefore, it's linear. Right. Next one. Be careful of examples like these because you just suddenly look and see, oh, there's an exponent there. It's bigger than 1, so it's not linear. Don't be fooled. Okay. Remember, this is for variables only. 8 is not a variable. 8 is just a number. It's a constant. So we're only looking at terms that contain letters. So I'm not even going to look at that. So this x has an invisible 1, and this y has an invisible 1. Okay? So the total value of exponents in this term, this is 1. We actually call this the degree. So we would say the degree of this term is 1. Same thing with this one. So it's linear. All right. Next one, we have 3 times u times v minus 2 equals k. All right, so this term has letters in it. So does this one. Okay, so this is an exponent of 1. That's an invisible 1. So the total, okay, of exponents in this term is actually 2. So the degree of this term is 2. Well, that's not equal to 1. So right away I know this is nonlinear. Okay, this k is okay. K, okay. That's an invisible 1. But as soon as we have one term, okay, that does not equal 1, then the whole thing falls apart. Okay, it's nonlinear. All right, lastly, y equals negative 6. Well, that pretty much is just like the first one. So I just look at any term with a variable only, and that has an invisible 1. Okay, well, the degree of this term, meaning the grand total of exponents that we see off of a variable, that's just 1. So that is linear. Okay, so as you can see, no graphing was necessary. I just counted exponents. It's that simple. All right. Now just to touch on something that was mentioned before, I talked about the idea of quantities being dependent or independent. All right, maybe you figured this out already, but I'll throw it in there anyway. In a relation, the dependent variable is usually, not always, but usually it's isolated, meaning it's the variable that is by itself. Okay, so for example here, okay, this relation that we discussed earlier, we have two variables x and y, but it's the y that is isolated. So I would argue that y is the dependent variable. X therefore is independent. Okay, if we looked at this one, okay, here the y is isolated, it's by itself, and the x is buried over here with a bunch of junk. Okay, so we say y is dependent, the x is independent. If you look at relations like this, well, let's look at this one. Okay, the 3uv minus 2 equals k. We have three variables. Okay, k, that's the variable that's isolated. So I would say that is the dependent variable, and both u and v are two independent variables. Okay, this one, however, well, that's kind of the odd duck. Okay, we don't have any variables that are isolated. So in this situation, it's not clear which one depends on the other. Of course, algebraically, we can try and isolate one of them. I would argue that p would be easier to do, but as is, it is not clear. Okay, but in this course, whichever variable is by itself, typically that's the one that's dependent. Okay, and when you graph it, the dependent variable runs vertically, up and down. And we know from an xy graph, vertically is the y, that's the x. Okay, so the independent variable, therefore it runs horizontally, which is why the independent variable between x and y is typically x, horizontally. There we go.